Okay, so I think we're going to get started, and we will allow the latecomers to join us as we progress. Welcome again to our statistics series for the EMDM, and today we're going to be talking about data collection and tabulation. We're also going to be talking a little bit about randomization and the process of randomization. I'm sure all of you were quite disappointed to see that there was no pretest to go along with today's session. And I hope also to not disappoint you because today we're going to have a lot less math than we have been talking about in the past few sessions. And our session today will probably also be a lot shorter than our previous sessions. So I apologize if anyone's disappointed by this. Objectives for today. Basically, we're going to understand the principles of how to randomize and how to take a random sample, and understand how to tabulate data for future statistical analysis. And again, we'll be following the same format. For any of you who are following right now, please feel free, if you have questions, comments, or thoughts, please send them out in the chat, and I will be happy to address them as we go along. It's always my endeavor to try to make this as interactive as possible. It's a little bit difficult in the video conference session, but I certainly welcome your comments. Okay, so just to review, we talked about this quite a while back. I'm going to think maybe 4 or 5 lessons back when I put up a slide that said, what makes randomization so cool? And just to recap, what was so cool about randomization? Well, we talked about selection bias. Okay, so we don't want to just pick all our friends or pick a group that is unique in some way. So we want to get a cross-section across different people in the group. It avoids confounding. We talked a little bit about that. If you do a study, for instance, on effectiveness of a certain type of disaster plan in your hospital, well, perhaps there's something confounding that. Perhaps your hospital is particularly suited to your disaster plan, and then the results we get cannot be generalized to other settings. So randomization can balance the group with respect to covariates. So that's either known things or unknown things. And you see that, for instance, in clinical trials of medications, where some of the known covariates can be the patient's age, their gender, but then sometimes there's unknown covariates, things we don't even know. Maybe certain enzyme structures, certain parts of their social status that we don't know. It's hard to balance those covariates, and randomization can allow us to do that. And then finally, number 4, which I think is really important, it allows us to assess causality. Right? So we talked about randomized controlled trials are really the only type of statistical design that allows assessment of causality. And that's what we like to know. Does one thing cause another? So you'll notice that we call these randomized controlled trials, not random controlled trials, but randomized controlled trials. And the important thing is this verb. This verb here is randomize. And we don't just say we take a random sample, we take a randomized sample, randomized experiments. Why? Because we actually need to do something to randomize them. Okay? We cannot assume that things are random when we just pick them up in the order that they come to us. We have to randomize them. So how can you randomize them? Well, there's many different ways. Some possible methods that you can randomize them. Well, you can flip a coin. If you have a statistical design that has 2 groups and you want to assign your subjects to one group or the other, flip a coin. We can use random number lists. I'll show you how to do that. Computer software, and there are some very slick and very easy to use randomization websites on the internet. These are 2 that I just picked up, but there are many of those out there. So we need to decide before we conduct our study which of these methods we're going to use to randomize our subjects, and we need to describe that very well in the methods. Okay? And the method that you use to conduct this randomization really largely depends on the complexity of the randomization scheme of your study design. There are several basic types of randomization. I think all of you will, when I put these, you might have trouble answering this question if I said what are the basic types of randomization, but I think most of us, when we see them, will recognize them basically as situations that you might encounter, and you might even know the name for them. Okay, so there's simple randomization, block randomization, stratified randomization, and covariate adaptive randomization. Sounds kind of complicated, but I'm going to show you how each of these four work and how we might attack the problem of randomizing these. So simple randomization is basically when you have equal probability of being randomized to any group. Okay, so this might be your groups that are getting 2 different medications or 3 different medications. Okay, and because we will be randomizing using a simple randomization, your group sizes will not necessarily be equal at the end. Okay, and you'll see that when you read studies of randomized controlled trials. The group sizes are pretty close, but they're not always exactly equal. And this simple randomization works well for really large sample sizes. It works very well. And it's also very handy for ongoing studies where the sample size is unknown. So you can imagine a study where you randomize people coming into your emergency department to be triaged by either START or your traditional triage method, okay, and to see which one is faster. And as each patient comes in, we would simply flip a coin. So we don't need to know ahead of time how many patients we're actually going to have in our study. We just go ahead and flip the coin. So here's just an example. A researcher is studying the effect of prednisone on the duration of infectious rhinosinusitis. And over the next 1 year, all the patients meeting the study criteria will be randomized to receive either prednisone or to the control group. Okay. So here we just pick a coin and we say, in Europe we use the obverse reverse terminology. We call them heads and tails in North America. And you simply, as each patient comes in, you decide at the beginning of your study, anyone where the heads comes up, they get the placebo, tails, they get the study drug, which in this case is prednisone, and you just flip the coin. Okay, and that's it. So you can see this is a perfectly acceptable randomization procedure. You would just write this in your methodology. As each patient entered into the study, a coin toss determined whether they were part of the prednisone or control group. That's very simple, works well. Their textbooks in statistics, particularly older textbooks before we had computers to help us out, often contained these random number tables, okay? And you can use those in any way you want. So in this case, we could basically just read down the column A and say, okay, well, all the odd numbers are control, even numbers are prednisone. So that would be another way you could randomize them. And again, you would need to describe this in your methodology. Okay, so that was simple randomization. And you can do the same thing for groups of 3. You know, if groups of 3, you would, for instance, roll a die, and say if it's 1 or 2, that's one group, 3 or 4 is another group, 5 or 6 is another group. Okay. Now, block randomization is used when we want to make sure that we get equal size groups. For this, we really do need to know the sample size at the onset. And this is to avoid, in small experiments, we want to maximize the power by balancing the group size. Okay? So you can imagine if you're doing small experiments, let's say that you have only 8 people in your experiment. I want to be sure I get 4 on one side and 4 on the other, because if I get 6 and 2, you can imagine that that small group of 2, we're not going to have a lot of statistical power in that group to make any assumptions. Okay? So we can use block randomization. So here's an example. Researcher is investigating the utility of a helicopter versus snowmobile for backcountry rescue in winter. And she has 8 volunteer teams who will perform a simulated rescue. She assigns 4 teams to the snowmobile group and 4 teams to the helicopter group. Okay, so small group, we want to make sure it's equal. There's a number of ways to do this. Almost all statistical programs will have this sort of very simple interface. So this basically is the statistical program that I use called R, and you just ask it to sample by taking 4 out of that group of 8. Another way you can do that is with these very simple randomization plans. Okay, so this is on a website conveniently called Randomization. And here you enter the treatment labels. So we have 2 treatment labels, helicopter, snowmobile, and we say we want 4 subjects per block. Okay, and basically you hit generate plan, and it just comes up with a plan. And then there's your 8 subjects, 1 through 8, and they go in that order. Okay. And so again, if you were using this type of randomization, you would just simply write in your methods. So basically what you would do is you would assign beforehand group number 1 through 8, and then you randomize them here and publish your plan here as part of your statistical methodology. Okay. And the nice thing about this randomization site is very interesting. You can, because each of these plans has a seed, you'll see this seed is 19435, other people can reproduce your plan exactly. So it makes it reproducible. It shows people that you are transparent in your methodology. Good. So that's block randomization, and it's really useful when we have small groups, when we want to make sure the group size is equal. The disadvantage being that we need to know at the outset the number of people in the experimental group or subjects in the experimental group. Now, stratified randomization, here things are going to get a little bit more complicated. In stratified randomization, we're balancing against a suspected covariate, okay? In other words, we think there's something in this group that will act as a covariate, and we want to get it out right away. I'll show you how this works. But you really need to know this covariate at the outset, and it can be really complicated if there are multiple covariates. And we really should consider this when there are obvious significant covariates, especially when the sample size is small. Okay, it sounds complicated when I describe it like this, but when I show the example, it's going to all make perfect sense. So you have 20 students who will be randomized to a simulation training versus no training and then a live exercise. Okay, so we can understand the study design is this researcher wants to know that if training will help these students in their live exercise. Okay, so you randomize them. The 4 students from each of the 5 years of residency training, and we're going to randomize half of them to the training group and half of them to no training. Okay, so you can see here we have 4 students from each of 5 years of residency training. Now, what we don't want is all the patients from the first year of residency training in one group and all the students in their 5th year of residency training in the other group, right? So what we want these groups to be balanced so that the overall experience in each group is similar, but still randomized. Okay? So I hope that makes sense to everyone. What we're looking for here is the covariate of number of years of residency training, because we're pretty certain that there's a good chance that your length of residency training will change your ability to perform on the live exercise. So we need a balanced but randomized group. There's some really, again, there's all kinds of ways you can do this. Here, I would either use one of these websites or I might get some help. If you've never done this before, you do want to make sure that you do this correctly, because if in the end you have two groups that are unbalanced because of the covariate, it's very hard to explain that in your discussion of your paper. Okay, so if at the end of this paper you find all the fifth-year students in one group and all the first years in another, it's very hard to explain that out in your discussion. So here's the thing called, website called Sealed Envelope, and you say, what are my two groups? Okay, and we say I have two groups. There's simulation and no simulation. And the strata here, which are the 4 years, year 1, year 2, year 3, year 4, and year 5. And you can see here that we want blocks, right? So we want blocks of, we said here we would pick 4 students from each of 5 years, right? Actually here I think yep, that's right. So they're blocks of 4. Right? And so they're randomized to by their year. So you'll see in that group there are 4 of each year, and they're randomized to simulation or no simulation, but balancing it out so that the two sides are relatively equal. And so these can get a bit complicated, and I think it's a good idea to get help. The thing that you need to know as a researcher is that when you look at this type of study design, that you say, okay, year of training is a covariate. I need to randomize in a way that will balance that, and then to either ask for help or check out one of these websites. And the last thing I'm going to just mention in passing, I don't think we need to use this, is this covariate adaptive randomization. You might see this written. It's useful mostly in big, rather complex trials. And this is where new participants are assigned to a particular group depending on the characteristics of those in the study. And so basically what you're doing here is you're adapting your randomization to the people that are already in there to make sure that the groups remain balanced for some covariates. Okay. You won't see this very often. If you do see it, it will be in, many of us probably have been involved in these trials where you see a patient and you are asked to enroll them in the study. And when you enroll them in the study, you have to either telephone or you put information into a website, different information. They ask how old is the patient, what's their gender, maybe some about their comorbidities, and the randomization is based on that. We don't need to do it, but you might see it out there. Okay. So just to share a little bit of my own experience where this can get you in trouble. I worked with a very, very enthusiastic student of the EMDM a few years ago who we drew up our study design together, and I said we would randomize the subjects to one of two groups, and this was a CTAS versus START triage study, and I said we would randomize them. The student was very enthusiastic and went ahead and basically performed the study without really needing any input from me. But in the end, the randomization procedure that he took was that as he approached these were a group of nurses, as he approached each nurse, every second one went to the different group. Okay, so the first nurse he saw, he said, will you be part of my study? He or she says yes. He said, okay, You're in the CTAS group. The second nurse, will you be part of my study? Yes. Okay. You're in the START group. And he just alternated CTAS versus START. Okay. It seems like it should be, in the end, we should get a relatively random group because you would think that the nurses sort of came in no particular order. But when he went to publish the study, the reviewers picked up on that very quickly and said, that is not a randomization procedure. At no point was a randomization performed. Okay? And we had to then go back and in the discussion of the study, explain what had happened, explain why it hadn't been, the randomization wasn't performed, and we had to explain what will be the implications on the study. Okay, so it ended up as, I would suggest, probably dozens of hours of work on his side, and it certainly weakened our argument in the paper. Okay, it was such a simple thing. All he needed to do was flip a coin. Instead, he chose them alternating. It ended up as a problem for us. Okay, so randomization, make sure that you use the verb randomize. We need to randomize them. Okay. And that's basically it about randomization. Get help if you need it. Make sure it's specified exactly in your study design. And if there's any questions about randomization, please feel free to pop them up on the chat now if you like, or at the end. At the end we will address that. Okay, so one of the questions, what if theoretically you ended up with almost everyone in one group in a coin toss? Okay. Yeah, Abdul, this is a very good question. This is why so theoretically you could, this is the problem, right? If you think of maybe you have 4 people in your study design, right? And so you imagine that you have 25, 12, you have like about 1 in 8 chance of getting them all in the same group, right? If you have 4 people, which is why you should not use a coin toss in those small groups. You should do block randomization. In a big group, if you have 100 people, the chance of getting a much bigger group than in one than the other is virtually impossible. Okay, I don't know what I would do. I guess I would panic if I accidentally flipped a coin and I got 100 of the same toss over. I guess it's theoretically possible. But you're right. That's why I really recommend the block randomization for small groups, because you want to stay out of that situation. Because you can't just reject your randomization because you don't like it, right? That takes the randomization out of it. So very good question. Reserve the coin toss for bigger groups. Okay, and so what we're going to move on to now is talk about data collection and particular data tabulation. Many of you are going to get studies that involve a massive amount of numbers when you're done. Okay, this is particularly true for any of you who are doing survey-based research, because the amount of data you get at the end can be really hard to deal with. And any of you who are doing sort of these pre-test, post-test type studies, or demographic studies. Those of you who are looking at, is there a difference in demographics between victims who develop infectious diseases after a disaster response and those who do not, and looking at their age and gender and social situation? You get massive amounts of data. Okay? And what are we going to do with them? So I suggest right at the outset, before you start tabulating your data in any way, think about how you are going to analyze it later. Okay. So how can we tabulate our data? And I think this comes from, this is not my quote, but it's a rule that computer programmers use when deciding what's program logic and what is data. And this is called the rule of representation, that says, fold the knowledge into the data so that the program logic can be stupid and robust. Okay? And this is the same thing for statistics. What we want to do is fold all the knowledge that we have, all the knowledge we collected into the data, so that when you do your statistical analysis or someone else does your statistical analysis, the logic behind it can be stupid and robust. Why? Well, you don't really, by stupid we mean that it should be easy enough for anyone to do your data analysis by looking at your data. Okay? You don't want to have to spend 2 hours describing your data set to someone so that they can do the statistical analysis. And it should be robust in that we want to make it so that it's difficult to make a mistake. Okay? Mistakes can be made by either the person. Okay? So if it's hard to understand what your logic is, what your data is, it can be hard to understand from looking at it what it is. It can be easy to make a person to make a mistake. And then it's easy for the computer programs to make a mistake for sure. Okay? So your computer program would love to calculate your average postal code, for instance, and decide whether the postal code is, if there's a statistical difference between the postal codes between your two groups. Okay? The computer would love to do that for you. We don't want it to do that, so we want to make sure that we fold it into our data, all this knowledge. Sounds complicated. It's actually just the opposite. What we're going to do is something so simple that it usually astounds people what we're going to do. Okay? So how can we tabulate our data? So people will often just draw it on a piece of paper. For really simple data sets, we can do that. We can use spreadsheets. So I'm a big fan. You'll see simply tabulating things on spreadsheets. Databases, it really depends on your level of knowledge. My preference always is to put the data directly into a SQL database so that you can manipulate them. If you're comfortable with that, that's a good way to go. If you're not, the knowledge curve of learning to use a database is usually not worth it, so I'd scratch that off your list. And then you can actually directly format your numbers and input them directly into the software. Okay, so SAS and R, which are the two most popular statistics software for statisticians, we can do that. And then there's others, like if you use SPSS or Minitab, you can directly input them. Again, I don't recommend that. The statistics software is really made for analysis. It's not really made for data collection. So that's not your best way. So this is what I recommend. Unless you are certain of which software will be used for the entire analysis, the best way to tabulate your data is probably on a spreadsheet. Okay? And then this data will need to be read into a statistics software package. Okay, so exactly. You can also export from Excel. That's what we're going to talk about. Thanks, Abdul. Thank you. That's a nice lead-in. I appreciate it. Yeah. So all common statistics software will be able to read the spreadsheet if it is properly formatted. And that's the big if at the bottom. Okay, so this is what I recommend. Unless you have some reason you need to learn to use a statistical software package, I do not recommend getting a copy of SPSS and typing your data into SPSS. Okay? There's no need to do that. We can do it on a spreadsheet, and then we can read that into our software. Okay? Unfortunately, this is a typical spreadsheet that I often get from extremely well-meaning students of the EMDM and researchers that I work with. Spreadsheet looks something like this, okay? And this is a huge problem, okay? So it's even hard really for me when I see this to understand what's going on, okay? So if I look at it, I see that there is 9 different cases, right? So those are along our column A shows 9 different cases, but there's 2 rows of 9, and it looks like some have done start and some have done CTAS, and then they're numbered across, and then there's times, And in the typing time, I see sometimes not recorded and no typing. Okay, and then there's some summaries here, some, I don't know what those are. Okay, so when you look at this, this is not easy for anyone to understand. And I think that anyone who tried to do an analysis on this would both be, would be both confused by it, and this cannot be read into a statistics software package. Absolutely, like Abdul says, we need slim and tall. What we need is a much simpler problem, a simpler solution. And I feel, I must admit, I feel terrible when I get these spreadsheets from the people I'm working with, because it's clear this took a lot of work, right? So you can see everything's all beautifully put in bolds, and it's justified properly, and it's in little blocks. I mean, someone really spent a lot of time putting the spreadsheet together, and I have to tell them, this is beautiful, but it's not going to work. You have to redo the whole thing, and it is not fun, okay? Revamping a spreadsheet is a really unfun procedure. It takes a long time. It's filled with errors, okay? So here, I'm just going to give you some tips for how to use a spreadsheet, okay? So the first thing is we use only one sheet per workbook, okay? So you'll see in this one, there is, this is just an example. This is one sheet of, it looks like about at least 6 or 7 sheets in this workbook, okay? So we don't do that. For statistical analysis, we have one sheet per workbook. We are going to save them in this .csv, which is the comma separated value. Okay, and all of your common spreadsheet engines, whether you use Excel or I think it's Numbers is the Apple one, or any, even if you use old school Lotus 123, you can always save these in comma separated value. The statistics software and most of your statistics packages will use old school DOS type file names, so there's no spaces or punctuation or special characters in the file name. And if you can, what I recommend is setting up your spreadsheet, okay, setting up the template with no data on it, and talking to the statistician in advance and say, this is my spreadsheet, take a look at it, will this work for you? Okay, so that's your table. And then how do we make, that's your spreadsheet, how do we make a data table? Okay, so we're going to use this very, very simple table structure, incredibly simple. The first column is your response variable. Okay, so in the data that we just looked at, that was the time to do your triage. Okay, so if you look here, what's going on in this, what we really care about is this thing that says time, and we're going to put that as our first column. And the subsequent columns are the factors. Okay, so I hope that all of you remember from a couple lessons ago, what is your response variable? What are the factors? Okay, in this study, the factors were such things as number of years in practice, prior disaster event, whether they had a previous START training session, whether they use CTAS or START. Okay, so you can see by, when you look at this view of the spreadsheet, it's actually really hard to tell which are the factors. Okay, which are the factors? We can't really tell. So in our spreadsheet, we're going to use columns for each factor. The first row in your spreadsheet is the factor names. Okay, and the names are short because they'll be used in the analysis. When you get your printout, you're going to have them all printed out. We don't use any spaces in them. We don't use any special characters. And the factor names have to start with a letter. Okay? So first column response variable. All the subsequent columns are factors. On the first row, we're going to give a name to each column. These are short names. And then each row after the first one is a single observation. So that's it. That's what your spreadsheet's going to look like. It looks incredibly simple. And now we're going to enter the data into the spreadsheets. Okay, so some things that will cause problems for you And some of these are not very intuitive. It might not come across your mind because if you're looking at the spreadsheet, it might not be problematic, but for the statistical software it is. If you don't have the data, leave the square blank, okay? So what you might find, for instance, is that you have a questionnaire where you score patients' agreement with this particular statement. We need an improved disaster plan. You ask your subjects to rate on a scale of 1 to 9 how important it is. What if your participant does not answer that question? Okay, just leave it blank. Okay, so we don't put a 0 in there. Okay, because that 0 would indicate that they have exceptionally poor agreement with your statements, right? Which is not true. So we don't leave a 0. Don't put any words. We just leave it blank. Okay, and if we do that, this is again about folding the information into the data. If it's blank, then the statistics software will simply ignore it. It won't use it at all to calculate the mean or the average or the standard deviation or whatever you do. Just leave it blank. We have to be very consistent with formatting, okay? So if you mean yes, then you should type into your spreadsheet the letter Y or the word yes, but only that and always the same. If you use true, someone agrees, true or false, then spell true the same every time because statistics software will consider capital T, R-U-E, true in all caps or true in all small letters as 3 different responses. And sometimes that's obvious. It comes out in your data analysis that you have made a mistake. Sometimes it can be hidden back there. So you have 10 different groups, but you find out later that 3 of them are actually the same word spelled slightly differently, and then your analysis is completely wrong. Okay? Don't use codes. Don't use 999 to mean too high of a measure. Don't use 1 to equal true and 2 to equal false. Okay, so this is Abdul actually. Abdul, you seem to follow along beautifully. I love the lead-ins you give me about what to talk about next. So, right, so Abdul asked, what about coding it? No, Abdul, you don't need to be sorry. I quite enjoy it, actually. It's fantastic. How about coding true to equal 1 and false to equal 2? Should we do that? Okay. So the answer is no, we shouldn't do that. And here's a bit of the background that you might not understand until you use the statistics software. So what's going to happen if we code a column as 1 for true and 2 for false is your software is going to want to take the average of that. Okay? It's going to see 1s and 2s, and it's going to take the mean and find out the mean is 1.7. Okay? And that's not at all what we want to know, right? So the mean trueness was 1.7. It has no meaning, okay? What we would like to do instead is keep those as T and F or true and false, and then our statistics software will know it cannot calculate the average. Instead, it's going to give us a frequency table, right? We talked about frequency tables a couple times back. It's going to tell us 40% of people answered true, 60% answered false. Okay. Can you do this if you code them? Yes, you absolutely can. But the chance of making an error somewhere along the line is amplified. Why? Because if you go back here, we are going to then have to rely on our program logic, right, instead of relying on our data. Okay? So if you put true and false, then no one else can make a mistake on that. You don't have to explain it. You don't find out later that you put true is equal to 1 and false is equal to 2, but someone who put in your data actually thought it was the other way, that true was 2 and false was 1. Okay? So we don't code them. And use letters, not numbers, for nominal categories. Okay? So we talked about categorical variables. So that's true or false. Right? That's a binary categorical variable. but also if you have 4 groups in your study, right? So you have 4 groups, 4 different types of triage, and they are CTAS, start, sort, and like another one, sieve, okay? So you pick those 4. It's much better to name them, okay? So I would call these groups, group start, group CTAS, group sort, group sieve, okay? Use their names or letters. Don't give them numbers, okay? So if you use numbers, 1, 2, 3, and 4, you run the risk of your software or your analyst believing that that was actually a numeric variable, okay? So your software is going to treat that the same way it would treat temperature, okay? Thinking that group 4 is somehow 4 times higher than group 1, okay? It's a bit complicated maybe the way I explain it, but you can avoid this whole problem by folding into the data using letters for categorical variables or names. Okay, so that was a lot of information. I think most of you know I'm a huge fan of checklists, and I use them in my own work for sure. At various stages of my statistical analysis, I break out these checklists, make sure I'm on the right track, and for sure I recommend them for anyone who I'm working with. Before you send me your spreadsheet, I'm going to say, please go to the website. So this is my website, MedStat Studio. Go to the checklist section, grab the data tabulation checklist, and go through it. Okay. And what I'm going to do now is just show you how I would apply this checklist to a revamped version of the data. Okay. So this was the same data that we looked at up here. Okay. So this is how it came to me from the student who I was working with, and I said, okay, I cannot use the data like this, and I want you to go to the checklist and reformat the data to look like that, okay? And I'm going to go through the checklist. You probably don't have it in front of you, but you can follow along and download this or get this at your own time. So the first thing is the sheet contains column names and data only. Okay? There's no tabulations, there's no summaries, there's no notes. Okay? So that's very important. Do not, on this data sheet, calculate the standard deviation and put it at the bottom. Do not take the average. Okay? Column names are unique, right? And there's no duplicates. So that's very important. So you see I have time, score, method, operator. They're all unique and they all no duplicates. You see that there's only one response in each column, okay? So you'll see, for instance, that method says here it's CTAS and the operator it's C1. If any of you try to sort of export from something like SurveyMonkey. Okay, so let's say you do your study using SurveyMonkey and you just download it to an Excel sheet, which you can do. You can export from SurveyMonkey to an Excel sheet. You'll find some very strange things in that if you have questions where people can answer more than one, okay, so perhaps your question is, what type of disaster training exercises have you participated in the past? And you write live exercise, computer simulation, tabletop, high fidelity simulation. And there's 4 answers, okay? And your participants are able to pick anywhere between 0 and 4 of those answers. When you download your spreadsheet, what you'll see is something very annoying, which is you will have something that says, for instance, past experience, and it'll have underneath it either something blank, or it may say 1, 4, or 1, 2, 3, 4, and you can't use that in your statistical analysis. You would actually need to break those up. Okay, so you'd break them up into tabletop exercise, yes or no, computer simulation, yes or no. high fidelity simulation, yes or no. Okay, so you see here there's only one response in each column, and multiple responses are split to multiple columns. Okay, categorical variables are coded as letters or words, not numbers. Okay, so a good example of that would be where it says operator. Okay, so the third column in is the operator. That's the person who did this. Okay, because in this case, each operator did 8 triages. So operator C1 is one person. One nurse was labeled as C1. And we don't want to call them operator 1, 2, 3, 4. You want to call them A, B, C, D, E, or in this case, we called them C1. Okay. Zach, oh, yeah, okay. Yep, Eric, you've got it. Good job, Eric, at pointing out a problem. Absolutely. I'm going to come right to that. Categorical variables are coded as letters, words, not numbers. Data is saved as a single CSV file. Okay, so you see at the top, says there, data.csv, and there's only one sheet on this workbook. Okay, absolutely. Column names are single words. They start with a letter, and they have no spaces. Okay, so you can see if you move along towards the end where it says, column L shows start training. Okay, so it says start training, one word, put them together. We can't have a space in there. We can't have a hyphen in there. It just says start training. Okay, you know what that means. Your analyst will know what that means. Don't leave any spaces or special characters. Column names really should match the data collection sheet or the survey. Okay, so if your questions are numbered 1 through 20, I call them Q1, Q2, up to Q20. Okay, it's not a good time to introduce a completely new word here. Okay, and the reason is it just makes it very difficult to backtrack if there's a mistake, right? So try to make the column names match your data collection sheet or your survey. Another thing on here is that numbers should be left as values and not converted to discrete values. So a common thing to do that might be with age. Okay, so you might be wanting to do a study that compares pediatric versus adult victims of disaster and see which of those have better accuracy at triage. Okay, so a study is trying to decide if pediatric triage is as accurate as adult triage. You have the age of each patient, and you are going to need to divide them at some point into pediatric versus adults. Okay, don't do that now. Okay, just put their age in, and then when you do the analysis, we can divide them up later. Okay, why? Because inevitably, when you classify your subjects by any type of discrete variable, right? So we're changing a continuous variable with its age into a discrete variable, which is pediatric versus adult. You're going to lose some data. And so a common thing would be to do the entire study. You send me the spreadsheet that says age, pediatric, or adult. I do the analysis. You submit it for a journal, and the journal says, what was the average age of the patient? And we go back to our spreadsheet, and we see on the spreadsheet we have only pediatric or adult, and we didn't actually record in our data tabulation what the actual age was. And now we have to go back and bring that data back. Okay? So it's very easy when we do the data analysis to turn the number, the numeric, into a discrete variable, to change age into adult versus pediatric. It's very hard to go backwards from pediatric adult to average age. Okay, so don't do that at this point. If you collect it as a number, just leave it as a number. And then the final one on my spreadsheet was the data cells are left blank if the information is not available. Do not use the words NA or the number 0. and my colleague who sent this back to me did a very good job, except on that one point, just as Eric pointed out, in G2, that NA should be replaced by a blank. Okay. So again, that's the checklist. It really summarizes everything we talked about in our session today, and I encourage you to use it on your own, and I always welcome your comments. Okay. Now, if you format your spreadsheet like this, basically no matter what type of statistics software you use, they will be able to easily import your sheet. And you can see it's pretty hard to make a mistake now. I mean, looking at the spreadsheet, it's going to be very hard. It's pretty clear which is factors, which are not. It's going to be hard to accidentally, there's no errors in coding, right? Because we wrote true or false, whether they were correct. Okay. And in the end, just to show you how easy this is to use, EpiInfo, if any of you want a really simple statistics analysis package that's free, I really like this EpiInfo, and you can just download it off the internet. It's free, and you can very easily just import by drag and drop. You can import an Excel sheet. In R, which is the software that I use, it's just that one line at the top, which says this command read.csv. It brings the entire thing in, and instantly you can see all the information that I can get about your data set just by importing it from the Excel spreadsheet. So I can tell you how many levels of practice there was just by looking at it. And you can see how there, it's really hard to get that mixed up. The logic is folded right into the data, so it's hard to make any mistakes. And then if you use SPSS, which is the most common, from what I can understand, it's the most common statistics software in published articles and mostly used by non-statisticians to do their analysis. So it's very commonly used. And you can look it up on the internet, import Excel spreadsheets or import CSV into SPSS. Just to finish up, if any of you are using statistics software on your own, a couple of tips that come from thousands of hours of statistical analysis on my part that have caused me massive amounts of time. Write reusable code, okay? Either write scripts or functions, and your code should read the data file each time, okay? Why? Because inevitably, this has happened to me so many times, you do your entire analysis and you find out that somewhere in the data a mistake was made, okay? So you go there and you find out that, oh, this one up here actually, where it was coded as NA, in the typing, it wasn't actually that the person forgot. It was actually written on the sheet, and the value there was 300. Okay, and you have to do your entire statistical analysis again. Okay, so what we do when we write these is we write a script that does the data analysis, that reads the data file, and so if you come to me and say my spreadsheet has changed, I say, no problem. It takes literally seconds to rerun the entire data. I highly recommend avoiding proprietary data formats. So that's inputting your data into, let's say you use a specific software package, and you put the data directly into there. Sometimes it can be hard to get it back out. And so you use Stata, for instance, for your statistical analysis. You put the data directly in there. Someone says, I'd like to repeat your analysis using SAS, and you have to go through the entire process of trying to back up. So I avoid these proprietary data formats. I use either the SQL database, or when I'm working with non-statisticians, I say, tabulate that on an Excel spreadsheet, and we can use it for everything. And just remember, I think, emphasized throughout our statistics course that we've been doing together that learning how to use the software is not the goal. Okay, software is very easy to use, but it provides you with multitudes of tests, and you have to make sure to know the right ones on how to apply them. Okay, so the software will very frequently do the wrong test. It will do a regression analysis using the zip code as a factor. Okay, the software is totally happy to use your zip code as a factor in your regression analysis. It's wrong, but the software doesn't know that. Okay, so make sure that you understand the statistics first before using it. Okay, so that wraps up our whirlwind session on randomization and data tabulation. I'm happy to field any questions right now. If anyone has questions about the data tabulation, or if anyone wants to share their own experiences of what worked and did not work for them. Otherwise, I will be, as always, available to any of you on the forum. If you have any questions, post them up. I'm happy to try to help you through that. And I'm available by email or through direct messenger on the EMDM platform for anyone who has specific questions. And so that sort of summarizes our objectives. We're to understand the principles of how to randomize. Again, randomize is a verb, and how to take a random sample, and to understand how to tabulate the data for future statistical analysis.
Yeah. Can I ask a question?
Of course.
Yeah. It is not related to the today subject. Actually, it is related to the last lecture. Thank you first for your nice lectures. The question is that in a study, we can have more than one test, like t-test and k-square test in one study, or it is necessary that in the one study only one test will be there?
Yeah, so that's a very good question. So you're talking about, from what I can understand, having multiple response variables, right? So you're looking at a study that, let's say you're looking at use of triage, and you want to measure, one thing you want to measure is the accuracy between different groups. Another is the time between different groups, and then another. Right, exactly. Okay, exactly. Okay. So
Thank you.
And you can think of a multitude of these. You can have studies that have dozens of response variables. Okay, so there's a couple problems with these type of studies. One is that they tend to be very weak in their power to discover differences between the groups. Okay, so when you add multiple response variables, the chance of getting an error by chance is increased. Okay, so because of that, you need to compensate for the fact that you're using multiple responses by using some type of correction. And I'm not sure if you can recall back to this. We talked about the Bonferroni correction way back, correcting your p-values for multiple tests. Okay, and you can do that. You can do that. There's sort of two ways around this multiple responses. One is, yes, you say the primary objective of my study was to measure the accuracy of triage. The secondary objective was to measure the time to triage. Okay, and so your primary objective here would be chi-square, right? The accuracy of triage is a type of chi-square test, and your secondary objective would be probably a t-test if you had two groups, okay? In which case you have basically two different response variables, and yes, you've used two different tests. That works pretty well if you have, if you have two different outcomes. if you have 10 different outcomes, it's really hard to justify that in your study. And what you will see is a lot of studies then move to these sort of all-encompassing endpoints, okay, or what they'll call combined endpoints, okay. So here's where you see a study that instead of the response variable being number of people to go to hospital, number of people to die, number of people to be readmitted in 24 hours, and number of people to need intubation, instead of calling that 4 different responses, we combine them into one combined endpoint in the study, and we say our combined endpoint was those 4 things: intubation, return to hospital, mortality, readmission. And then you do a single test, maybe your chi-square test, on that combined endpoint. Okay, so this is all the possibilities. The best studies that you see in the literature have one single hypothesis, one single endpoint. Okay, even the big studies, if you look at the big cardiology studies, the big neurology studies, neurology and cardiology probably do the biggest studies in sort of in emergency medicine, they usually have a single endpoint and a single test. For your thesis, knowing that your thesis coordinator, Joost, he is going to be happier to see you choose a single endpoint and to work that out, maybe have a primary and secondary hypothesis, but probably would prefer that to these studies that have multiple endpoints. Okay, so very good question. I hope that addresses what you're asking about. I can elaborate on a little bit further, or if you have a specific example, I can answer that too.
Thank you, Professor. Thank you.
You're welcome. Okay, so I think we will wrap things up here, and I look forward to seeing you. We have, I believe, 3 more sessions before your final exam. And then after your final exam, there will be a couple optional sessions where I can help any of you who are having trouble either tabulating and plotting your data or writing your paper, particularly those of you who are not first language English. I'm going to give some tips on how to write a paper in English. Okay, thank you very much.
Thanks.
Jeff?
Yes.
I just came around because I might have a question regarding the previous session, not this one. So I don't know whether I need to wait a little bit after this one, or I call you later, or we can proceed.
Either way, I can try to answer your question now. It's not a problem at all.
Okay. You remember last time we discussed correlation, and you provided us with a sample. I think it was thousands, maybe 2,000 or 20,000, a number with 2,000 or 20,000 numbers, something quite huge. And
yes,
in the end, it was the correlation was significant, but it was the correlation was, if I'm correct, 0.5, no 0.05, something like that. So something very close to 0, meaning it was significant, but the magnitude of the correlation was such that, and you said because the sample is huge, we can't interpret. You remember it was between blood pressure and pulse, something like that,
yep.
If I'm correct.
Yep, absolutely. Yeah, I recall correctly. Yep.
And you said because the sample is huge, we can't say that it's significant statistically, but clinically it doesn't. We can't interpret, or we can't extrapolate on it. I would like to know whether, because I'm using correlation and my sample size is quite very low in comparison. It's more about 50 numbers with 50, something like that. And so I have significant correlation, and the correlation is about, sometimes is about 0.4, between 0.4 and 0.5. And I understand that when it's below 0.5, it might not be, it's significant statistically, because it's below 0.5 or 0.001, but because the number is, I don't know how to extrapolate between your example where you have a large sample and my sample where I have only, the number is only between almost 50. So I don't know whether the number of the sample could influence the interpretation of the results. If we are close to 0 or close to 0.5 for the correlation, does it impact the interpretation, and how?
Okay, for sure it impacts the interpretation. So I think the best way to look at these is that the statistical significance and the clinical significance are two completely different things. Okay, so in your study, you've shown that for sure there's a correlation, right? Your p-value says the correlation coefficient is not 0. Okay, it's bigger than 0. Okay, we know that. Now, the question is it meaningful enough to be useful in any way? And that's where you notice, you remember I plotted my correlation. I drew a plot of, on the one axis was blood pressure, on the other was pulse, and I said, well, plot them, take a look at them. Do you see a trend that might be useful? So the first thing I would do with your data is plot them and take a look. If you look at the graph and it says, oh, clearly you can see a beautiful trend there, then it might be useful. If you can't, then often you say the same thing. It's statistically significant, they're correlated, but whether it's important or not depends on what you're going to do with it. Okay? So if you're using it for, say, clinical prediction, okay, so say you were going to see, is there a correlation between being on an airplane for 8 hours and getting a pulmonary embolism, okay, for instance. Well, if you want to make clinical decision work, you need a pretty strong correlation for it to be helpful for you to make a clinical decision, right? Okay, because you can't be influenced by a sort of weak correlation. On the other hand, if you're looking at the correlation between, let's say, for instance, Guillain-Barré and vaccination, where you're going to be applying a vaccination to millions of people, well, even a small correlation may in the end up with an increase in cases in Guillain-Barré, and therefore that small correlation is important. So what you're probably going to need to do in your study is explain what is the clinical, or maybe clinical is not the right word, what's the practical, medical, clinical importance of this correlation and how you're going to use it. So it becomes not a statistical argument, but a clinical argument. Does that make sense?
Yes, it makes sense. Okay.
A very complicated thing that I can mention to you, another way of looking at this is that your correlation coefficient also has a confidence interval associated with it. Does that make sense? Oh, did I lose you?
Yes, it makes sense.
Yeah. Okay. So your correlation coefficient might be 0.5. Okay. Let's say it's 0.5. But if the confidence interval goes from 0.1 to 0.9, it's still significant from a p-value point of view. But then you have to say the correlation could be as low as 0.1. In which case it's not very significant. Could be as high as 0.9, which case it's very significant. And so that is something also we haven't talked yet, and we will in the next lesson about what confidence interval means, how to work that in your study. But that's something you can look at as well when you're explaining the significance of looking at the confidence interval for your relationship. And you're someone can help me from that. I can tell that from that. Or whoever suggests can help me from that if that might be something to add to paper.
Yes, okay. It clarifies a lot, okay.
Okay. Okay, thank you very much for your comments, Eric. I always enjoy your questions and comments. Thank you.